Okay, everyone, let's get started. Today we're going to keep talking about convolutional neural networks, as we didn't finish the subject last time. So since we postponed or extended the deadline for your project proposal, I'm going to release the third programming assignment today, right after the lecture. Actually, I need to finish a couple of details, but probably in 2 or 3 hours, you should have that ready to get started. I'm going to put the deadline by one and a half weeks from now, so that should be fine. There is a slightly modification here. So I'm not going to give you those comments where to put your code anymore, okay? So I'm going to give you some sort of like interface to actually write your code. I'm going to give you the test cases. But this time, test cases might not match 100% because, and you still might be writing correct code. But since you're going to have more freedom to design your own networks, the test case, they'll be more like a guidance than actual, like, oh, it has to match perfectly that result, okay? And at the end of the programming assignment, you're going to have a challenge. So the assignment is about training a convolutional neural network for handwritten digit classification on using MNIST. And I'm going to give you some guidelines to get to a certain accuracy, which is going to use one architecture we're going to see today, which is LINET5. But then, as a challenge, I'm going to let you try to improve that. And whoever gets the best accuracy is going to get 1 extra point. Okay. So hopefully that's going to motivate or give some extra motivation to not just fill out the code, but actually try to get better performance out of like just being creative. Okay. And whoever gets to the so there is, I mean, you're going to get full grade if you finish the whole assignment. I'm just giving an extra point if you, for whoever gets the best accuracy for this challenge. So last time we were talking about convolutional neural networks. We started with the ideas of filters, and then we saw that we can use filters with convolutions, right? And then these convolutions, they have certain properties like padding and stride, or you can see them as hyperparameters that you can tune to get different outputs. And we saw convolutions over volumes. I'm saying volumes here because, so first we start with an RGB image normally, which has 3 channels, so it's still a volume. But then you saw that as you keep applying these convolutional layers, we keep getting different volumes with different depths. So we saw how to apply convolutions to these volumes. And then we saw a very first CNN architecture, which we're going to develop today to get to LINET5, which is this very classic architecture. And then we're going to see some other ideas. So first of all, we haven't covered the basics of convolutional neural networks because we are missing pooling layers. Pooling layers are very common type of layer that you see in modern convolutional neural networks. And we're going to see that there are 2 major ones, max pooling and average pooling. And in fact, actually, max pooling is the one that is mostly used today. And then, well, that actually finishes the kind of like the tools you need to build modern CNNs. They are mostly composed of this convolution layers followed by pooling layers. And then we're going to see some classic CNNs, like LINET5, which we're going to use as a basis for the assignment. AlexNet, which is perhaps the big bang of deep learning, and VGG16. Those are considered classic networks because they kind of follow the same procedure. They are just bigger and bigger. Obviously, there are differences. They came up in different moments in history, but to some extent, they follow the same procedure of designing CNNs. They are just bigger. compared to the previous ones. And there is a more modern neural network that came out, I think, in 2015 or 16, which is called residual networks or residual neural networks, which applied residual connections to make these convolutional neural networks even bigger. So, and if you like this topic, you should definitely take, there's a course dedicated to computer vision with neural networks in the department. I guess Michelle teaches it, so if you haven't taken that class, I guess from this lecture on, you'll see more modern, even more modern approaches to what we've seen in this course. We don't have time to cover the whole field of computer vision. This is not the goal of this course, okay? And also there's many other type of tasks. So we've been talking about image classification, which is a fundamental task for computer vision, but there is any other types of problems. As we kind of touch upon some of them, like object recognition and others, but yeah, this is the extent that we're gonna see convolutional neural networks in this course. And I guess they're gonna give you a good basis for working on computer vision models, even if you don't take more specialized courses. Any questions before we start? Okay, so let's start with a review. We stopped here last time. We saw this very first convolutional neural network that takes as input an image, which was 39 by 39 by 3. And then we saw that each arrow in this diagram represents a convolutional layer, right? And the blocks themselves are the activations, right? And then we see, like here, we see that the activation 0 is the actual input image, but then activation 1 is the result of that very first arrow there. And the result of that convolutional neural network is a volume that I think I didn't mention this last time, but I was talking about original image. I was using this nomenclature, right? Original image, and then kind of convolution. Then you'd have a transformed image. This is a nice way of seeing transformed image. It's a nice way of seeing the result of convolution as a transformation, but in computer vision, people call this output a feature map. Okay? So that volume that you see there, we can call them also feature maps. Okay? Because you're extracting features with convolutions. Okay? So every activation is a feature map that is a result of this convolution. And normally you annotate the arrows with the parameters of that convolution. So for instance, that very first arrow there has a filter size f1 equal to 3. And then there is a stride of size 1, a padding of size 0, and then there's 10 filters there because there's n1 equal to 10. And then we saw how to compute both the width and height of that feature map, also the depth. The depth comes right from the number of filters. Okay? So you can apply that logic and keep applying convolutions to this initial image. And that's going to give you a final feature map that normally, as we'll see in the next slides, they normally decrease in terms of width and height and increase in terms of depth. Okay, so if you see there, the image starts with width and height 39 by 39, then it decreases to 37 to 37, decreases once again to 17 by 17, and then once again to 7 by 7. But if you look at the number of channels, right, they start with 3, then they go to 10, 20, and 40. So they're increasing. Right? So this is a pattern that you see even today in convolutional neural networks. Okay, but then once you keep developing or convolving your image, at the very end of your CNN, we're gonna eventually, you're gonna flatten that feature map to create a feature vector. And that's going to go, and it's going to go into a feed-forward or fully connected neural network. And you can have as many layers as you want to get a prediction. Right? Any questions about this design here? Oh, sorry. We've been using this idea of convolutions with the goal of reducing the number of parameters. And here I just want to give you some arguments why. I mean, we saw that mathematically that works, right? We saw that we reduced the amount of parameters quite a lot. But just to give you some more intuition of why that helps. When we use convolutions, we are sharing, right? For example, a certain filter for different regions of the image. Right? And we briefly talked about this last lecture. So what you want when you train a convolutional neural network is to train filters that work in different parts of the image. Because in fact, like if you're thinking about face recognition, right? You want to have, at some point, you're going to have to learn a filter that detects eyes, and the filter that detects the left eye is the same filter that detects the right eye, right? You don't need two separate filters for the same task because it's exactly the same object, just it happens to appear in different parts of the image. So you want to share this filter across different regions. And if you learn a good filter, it's going to actually give you meaningful outputs, right, for different regions of the image. And if you think about this idea of connections, getting back to multi-layer perceptrons, to produce an output for a layer, you don't use now all the inputs of your layer, right? Remember when you worked on the programming assignments, you had to flatten that whole matrix to give as input to the multi-layer perceptron or logistic regression, right? So now we don't have to do that, which means we don't need to use all the inputs or all the pixels to give one output. Now we can have multiple outputs or separated outputs for different regions of the image. And that, in fact, helps reducing the number of parameters. This is just maybe to help argue why convolutions really help for reducing the number of parameters. Okay, so now we have to finish the tool set for building CNNs, we have to talk about pooling layers. And besides convolution layers that we saw, or convolutional layers that we saw last lecture, CNNs, they typically also have what we call pooling layers. And pooling layers are used for two main reasons. So first, you want to reduce the dimensions of the feature maps. Like remember, the activations, we want very frequently want to reduce that size. And related to that, as I think that connects to your question, we want to summarize the input in a smaller structure. Right? So, and pooling layers will help to do that, and they will do that actually explicitly by using fixed computations. So, and it's in bold here, these type of layers, they don't even have weights. They're not learned. They are predefined computations that we add to help extracting features from input images and then consequently feature maps later in the network. So there are two types of pooling layers that are mostly common, max pooling and average pooling. Okay? And as I said, these don't have filters that have weights in it. They're going to do predefined computations. Okay? So let's look at the max pooling first, which is the most used pooling layer nowadays. So it's a very basic idea. So here we have a 4x4 input image. And then what max pooling is going to do is you can think of it as a filter, but it's an empty filter. It doesn't have weights in it. Okay. And this is a 2x2 max pooling filter. Okay. It also has a filter size. Now it happens to be a 2x2. But what you're going to do is you're going to slide this filter or convolve it the same way we did before. Okay? But every time or at every convolutional step, you're going to just look at all the pixels inside that filter and you're going to extract the max out of it, the maximum value. So in this case, we get 9 as a result because 9 is the maximum from 1, 3 to a 9. And then we have a stride to the right, and here there's a stride of 2. Okay, I skipped, or that window was lighted by 2 steps at a time. You could do it at like 1 by 1. Okay, but in example, I'm doing like a stride of 2, and now I repeat the process. Now the maximum value is 2. Okay, and it's a simple convolution. So now I slide down. Since I reached the end of the columns, I slide down, and I get the maximum out of those 4 pixels now, which is 6. Okay, and then I finish with the last step, which is 3, right? The maximum value. So this is an interesting idea because, as I mentioned, pooling operations are meant to summarize an input. So by doing that, I'm somehow just looking at the values of my input that are higher. So I'm saving just that. Okay. So here, max pooling and also average pooling, they have these 2 hyperparameters, which is the filter size and stride size. And these are very popular values, like max pooling of 2 and especially stride of 2 in small images, or doing this even choice, as you will see later. But it's a hyperparameter you have to pick. Okay. I didn't talk about this last lecture, I guess, but picking a stride, for example, different stride values, might depend a lot on, for example, the size of images you're expecting in your network. Say if you have a very, very large image, you can pick a large stride size because, I mean, large images, they are just, imagine like a 4K image, right? We don't need that bigger of a resolution to understand what's going on in the picture. It's just a more clear picture of a dog, right? You don't need 4K pixels to understand that that is a dog, right? So by making a large stride in a very large image, you're just going to slide faster on that image, right? You're going to do a convolution faster. You don't have to do like one step at a time because that's not going to give you a lot of information. It's just like more details of the same thing, right? So picking these hyperparameters really like also have to do a lot of like the size of the images you are talking about and what they do, what they represent. Maybe you're trying to process images of the galaxy, right? And then you have these 4K images, but every pixel really matters because you're looking at stars and they're very small. So like the very basic detail of the star maybe really matters. So you have to, in fact, do a stride 1 by 1. But if it's like pictures of animals, maybe that detail doesn't really capture much, right? So it's a kind of an art, right? And you have to be creative. You have to think about the problem, like what the pixels are representing, and actually try out different values, right? So don't be frustrated. It's going to happen. Like you're going to try different values. It's not going to work. But then eventually you're going to have hopefully, you're going to have an aha moment and find out, oh, okay, yeah, this might be a best approach, right? So there's no single way of doing this again. And as I mentioned, there's no weights to learn here. Okay. And average pooling is similar, right? It's exactly the same thing, but instead of taking the max, you're going to take the mean. So here, hopefully the numbers are right. If you convolve now the average pooling filter, you're going to sum 1 with 3 plus 2 plus 9 and divide by 4. That should be 3.75, but I'm not 100% convinced. So you're going to do that for every single convolutional step. And that's going to give you a smaller image because it's a convolution, right? One thing that is interesting here is that if you use a stride of 2, right, you're going to see that a pooling layer is going to actually decrease the size of your image by a half. Right? So it's a very drastic change, right? But again, the average kind of gives you this intuition as well that what these pooling operations are doing is actually just condensing the whole information, right? So you take the average and you're summarizing that region of the image with the average of the pixels, right? And the same for each region. So you're just summarizing that. And that's the whole idea. And here you also have the same hyperparameters, filter size f and stride s2. Again, no ways to learn here. Same principle. Turns out average pooling is not as popular these days. Okay? Most recent neural networks or convolutional neural networks tend to use max pooling. Okay, so here's an exercise. Let's do this together. Let's apply a max pooling filter with f equals to 3 and stride of 1. Okay, what is the result? What is the size? This is a 5 by 5, right? It's a 3 by 3 image. How do you know that? But yeah, you're basically going to have, this is a 3 by 3 max pooling, right? So you're going to basically start with the filter here. This is a 3 by 3. So we pick the max out of this, right? Which is what, 9, right? And then we slide it by 1. And then we are here now. And this is a 9 again, right? And now we slide it by 1 again. And this is 5. Now we are at the end, so we go back and place it here. Again, 9. 9 again, right? The next one is going to be 9 again. So now you slide it by 1. Now this is 5. And let's last row 8. Six and 9. Right. This is very simple, right? But what I wanted to look at is look at the number of 9s that we got here and the number of 9s we had here. Right? We had only 2 9s in this original image, and now we ended up with a bunch of 9s here. So what max pooling does is really highlights these maximum values. Okay. So if you have a high intensity pixel, that's gonna, this max pooling really is gonna detect that. Okay. And kind of summarize this image by this feature map. So we call this a feature map. Okay, so one quick thing to note is that when you're applying pooling to volumes, we don't apply it as we did in convolutional layers. Now, so before we would slide a whole cube over that volume, and that would give us one channel. But now we're going to apply the pooling layers. They are applied individually to their respective channels. So the filter still has to match. You still have, if you have a 5x5x3 input image, your filter still has to have that 3 channels at the end. But each channel is going to be applied to each respective channel in the original image. So you're not going to mess up with the number of channels when you apply a pooling layer. Okay. That's a specific property that is important. So even though we are, just to keep in mind, even though we are summarizing the channels, we are doing that independently. We are not using the max pooling to summarize the whole volume. We are just summarizing each channel of that volume individually. So it's a less impactful summarization. It would be much more harsh if you applied and summarized those 27 like there's here 27, right? So if you apply this filter here to that volume, you're going to look at 27 numbers at once. We are not just picking the max out of those 27. We are applying this 9 filter here, looking at these 9 numbers here, pick the max, and then look at the green channel, which is the maximum there, and then look at the blue channel, which is the max there. So that's going to give you 3 maximum values, red, green, and blue. Okay. So this is a LeNet 5. This is a very classic convolutional neural network designed by Yann LeCun, which is a very famous deep learning researcher. And this was designed in 1998. Here at the bottom you see the original paper. And the image there is very similar to this. The sizes should match what is in the paper. And this was designed for handwritten digital declassification. And I really encourage you to look at this paper. It might not be the easiest paper to read, especially because the technology they were using back then, some of the things we don't use anymore. They're not very popular these days. So for instance, I'm going to start from the end here, but if you look at the paper, they don't use a softmax at the end. It's a different classifier, okay, that people don't use these days anymore. So then you might be asking, okay, why they are doing that? Because that was popular back then. But then you have to understand that, and this makes the whole paper kind of harder to read because you keep asking questions that you don't know, and then that makes it complicated. But besides this, I guess the whole architecture is the same. Let me actually open the paper so you.
I guess they use more activations in the middle.
Yeah, there is a bunch of details like that. For example, ReLUs didn't even exist back then, so they were using sigmoid activation functions and tanh. But here's the paper, gradient descent, graded based learning applied to document recognition. Very seminal paper, Yann LeCun and others, especially Joshua Bengio here, one of the Turing Award recipients for deep learning. Also, so LeCun, Joshua Bengio, and Jeff Hinton, they won the 2016, I guess, Turing Award. So yeah, very important people. So if you look at this paper, it looks like an old paper, right? You see that even the typeset here is like a little weak, but there is an image here at some point that shows the network. Yeah, there you go. Here it is. So what we're reproducing there, oh yes, is this image. And as I said, and as I told it last lecture, most CNN papers will have an image like this. They'll have a diagram showing the structure of the network. Just one quick thing is, as I said, for example, if you read here Gaussian connections, right? You might not know what that means. So that's a different type of classifier that people used to use back then. Nowadays, people use a softmax here. But of course, the paper doesn't discuss that. So it makes it harder to read, in my opinion. More recent papers are easier, in my opinion, because they use the terminology we know today. And they use the technology we know today. So it's somehow easier, especially like talking about deep learning, that there's so many people talking about deep learning today that you hear something there, oh, dropout. You might not know what dropout is, but you know it's something that exists nowadays, people use, it's very common. You might not understand the math behind it, but you trust it. Okay, this is good. But some things you don't know might make it hard to understand. Especially like the way, there's something that is a little bit weird here is also like how they apply the filters. So they don't have the filters match the number of channels of the input image. They have a very clever way of like applying different filters to an input image. That's not that common today anymore. So it makes it a bit harder to understand also like what's going on. So, but I encourage you to read, or at least take a look, try to read the paper. It's a seminal paper that is foundational for CNNs. And Jan LeCun is actually the head, the director of technology of Meta today. So he's still doing really great work and influencing deep learning to this day. So this is LeNet5. It takes as input an image that is 32 by 32 by 1. So it's a grayscale image, black and white. And it has 2 layers, okay? We normally talk about a layer being a combination of a convolution and a pooling, because pooling doesn't have weights. So we tend to see that as part of the same layer, because layers are kind of like this set of weights, right, that we can see as one separated set. Since pooling layers don't have weights, we tend to kind of group them with their next convolution layer. So we have this first convolution that is filter size of f equal to 5, and then stride of 1, and it has 6 channels. So you see that the first activation there is 28 by 28 by 6. And then it's followed by an average pooling. Back then, average pooling was quite frequent, but nowadays you don't see that average pooling anymore. It's still possible, it's just not common. So then see how, because the filter size of the average pooling is f1 equals to 2. I should use different maybe subscripts here for conv and average pooling, but the filter size for that average pooling is 2, and the stride is 2. So it's exactly the same as we saw. It's a filter size of 2, sliding 2 steps at a time. So that's going to shrink your image by a half. So that was 28 by 28, goes to 14 by 14. Right. Still six channels. Remember, as I said, like we apply the filters to their respective channels. So that average pooling layer kept the six channels in there, just shrank the size of the image. And then there's a second layer, which is also like a convolution followed by an average pooling. But now the convolution is still, the filter size is still 5. The stride is still 1, but now that should be n2, sorry. That is, now is 16. So now, as a result, in your average pooling, or second average pooling, the image becomes 5 by 5 by, as a result of the convolution 2, you get a 10 by 10 by 16 because of those 16 channels there. And then now the average pooling gives you a 5 by 5 by 16 because that average pooling is exactly the same as the previous one. Again, there's no weights in here. Okay? There's no weights here, there's no weights. Or actually, let me point to the arrows. There's no weights associated to this arrow here and this arrow here. Okay. But then the result of that second average pooling becomes a vector. If you multiply 5 by 5 by 16, that should give you 120. Oh, that's 25 times 16. Hopefully that's right. No, that's 400, right? It's 400 inputs going to a 120 hidden layer, okay? So that gives you a 120 by 400 matrix, okay? And then that's followed by a 84, or another fully connected layer, FC4, that has 84 hidden units. And then at the very end, as I said, nowadays you would have this softmax neuron to do classification, which would have just an output of size 10 here, okay? This is not the size of the matrix, right? This is the size of the output, which is 10 because the task here is handwritten digit classification. We have numbers from 0 to 9, or digits from 0 to 9. Okay. So as we saw, this is very similar to what we had before. We just plugged two pooling layers in between the convolutions. And that's answering the question from before. Yeah, that's what we normally do. We normally run a convolution and then a pooling operation, okay? As we will see, this doesn't have to be the case. You can have a convolution, pooling, right? You can have that. So, and there is modern networks that do that. So. Okay. Wait, I went up. So here's a summary of the LeNet5, or an analysis, let's say, a table with where the rows are the layers and the columns are different attributes of those layers. So we can think of these layers in terms of activation shapes. Those are the numbers we saw on top of the diagram, right? Those are the size of the activations, or the shapes. We can think of the size, which is just multiplying those three numbers, 32 by 32 by 1. That should give you 1024. And then you can think of also the number of parameters. And I'm not sure I didn't review these numbers, but I'm not sure they're exactly right. I'm going to check that after the lecture, but they're almost right. I'm sure about that. So if you look at the convolutional 1 layer, obviously, let's look at the last column, because that's what matters the most for the sake of this lecture. If you look at the input layer, obviously it doesn't have any parameters or weights, right? But then convolutional 1, the very first convolution there that has a filter size of 5 and a start of 1. And then we can compute the number of parameters, and we have about 208. Probably that's a little bit different, but it's about that number of parameters. So it's not much, right? At least compared to the bottom here. If you look at the bottom, you get way bigger numbers. So the second convolution layer, or the average pooling one there, the third row, doesn't have any weights by definition, right? And convolution 2 has 3,208 number of parameters. And then we have average pooling 2, which doesn't have any parameters by definition again. But look at the bottom here. So those fully connected layers, they really add parameters to the network, as we already discussed, right? Because now we have these weight matrices that depend on the input, right? So that very first fully connected layer there, FC3, has 30,000 parameters, just that layer. Okay. So yeah, this should be 400 by 120. How much is that? Anyways, so this LeNet5 network in total has roughly 60,000 parameters, okay? And it's a small network for today's standards. Very small, in fact. Let's look at a much bigger network that for today's standards is not that large anymore. It used to be like 10 years ago used to be our benchmark in terms of this is one of the largest networks we have. So this is AlexNet. And surprisingly, it's not as different as LNet5. And today we call this a classic network because it was kind of the very first network of the modern era of deep learning. Oh, we already discussed here that in LNet5, as I said, ReLU didn't exist here. So ReLU activations didn't exist at this time. So the activations function, the nonlinearities here, they were sigmoids and tanages. One key difference between LNet5 and AlexNet is that here you have ReLUs being applied. And this is the very first, one of the first papers at least, that use this activation function because it helps making the network bigger, okay? So AlexNet, first of all, it's also a very seminal paper. I do recommend reading. This is much easier to read compared to LNet5 or the previous paper. One reason is because it's more recent, but also because it's well written. And it's an applied paper. They're trying to win a competition. Right? So their goal is to make their accuracy better at that ImageNet competition. Right? So in 2012, they won this competition, and that made everyone in computer vision start to really believe in deep learning. And then that had an effect on other fields of AI. Then other people in natural language processing started to really believe in this idea. And then that became a snowball. And then we are here now studying these things, right? But these technologies back then used to be specific to really a few bunch of computer vision researchers. Right? Now this is everywhere. People are using this for anything, to be honest. And the idea here is now you have a much larger image. So ImageNet is this large data set which originally had about 40 or 50 million images, but that was too big. So they reduced it to 1 million images and made a competition out of it. So it's about 1 million images, 1,000 objects, or 1,000 classes. And the images are that size, 227 by 227, and they are RGB. So this is already a difference between LNet. It's a considerably larger image with more than one channel. So the network is as follows. So it has a convolution followed by now one key difference is now using max pooling instead of average pooling. Right? And then you have a second convolution followed by a second max pooling. And then you have this sequence of 3 convolutions here, conv 3, 4, and 5. And at the end you have a max pool again, and then 3 fully connected layers and a softmax with an output of 1,000 now. So that's 1,000 outputs here because there's 1,000 classes. And one thing to keep in mind, this is a much bigger network. It has about 60 million parameters. That one has 60K. Right, so it has much more, or many more weights to be trained. This makes it much harder. So if you read the paper, there's a bunch of details there, and ReLU is one detail they added to make this easier to train. Right? As we touched upon this discussion, that the larger your network grows, or the deeper it grows, the harder it is to train it, because you have to compute the gradients of the loss function at the very end with respect to the inputs in the very beginning. So the more layers you have, the more of those nested multiplications of chain rule you're going to have, right? And that tends to either explode your gradients or really shrink it down to 0. So in practice, it's very hard to train very deep neural networks, even though in theory, that is not an issue. So in theory, you could have as many layers as you want, but in practice, that doesn't work. So they had to keep changing things to help flowing these gradients, and ReLU is one of them. There is also the introduction of GPUs here. So these networks were trained with graphical processing units. That also makes the whole training process much faster than it used to be. Okay. And in terms of sizes or filter sizes, right, it varies. Here you have convolutions that have 96 filters. So then it increases to 256, right? Then 384, then goes back to 256, right? And that's the end of the convolution layers. Then you have a sequence of fully connected layers. So the filter sizes also vary a little bit. I didn't put them here because it doesn't fit in the slide. But let's try to take a look at the paper, see if we can look at the original image. And it's good for you to have that in mind, because again, this is a very seminal paper. You should be able to recognize this paper just from the first page. By the way, this is the main author, right? Alex Trishevsky. All right, but let's look at the image of the architecture. Oh, so the architecture is here. But here, if you want to take a look at the sizes, this is a 3D visualization of the CNN, which is also very common, because here you can see the filter sizes, like 3 by 3, 2 by 3, and the sizes of the volumes. And so, yeah, this is the actual figure that presented the paper. And here you're going to have, oh, this is interesting. Here are some, here's when, these images here, is very, there are visualizations that I mentioned. When you look at the kernels and you look at them as pictures, you can somehow understand what they are trying to learn. So for example, you can figure out that this kernel, he is actually learning a kind of a corner edge detector kind of thing. Right? So these are probably lower kernels from the beginning of the network. So what does it say? 96 convolutional kernels of size learned by the first convolutional layer. Yeah. So in the very beginning of the layer of the network, it kind of learns the lower level features. And as you kind of, if you visualize the later filters, they are more higher level concepts like eyes and faces. Not sure this is in here of the paper. But yeah, here you're going to see some results. And yeah, they even have some qualitative analysis here, which is interesting. Anyways, let's keep going, because I want to finish this, and then we maybe can discuss the whole thing at the end. Here's another one that is good to study, because if you look at AlexNet, there is all these hyperparameters that are different. So they have different filter sizes for different layers, and they pick that kind of empirically, so it's hard to discuss why do they have a filter size of 5 in the layer number 3, for example. So they had different setups for different layers. And then it was hard to know like what was actually making this work. So this network, VGG16, and there's different versions because that's why there is a 16 in there. But there's this paper here that shows that you can actually simplify these things and this will still work. Okay? So in some way, VGG16 simplified deep CNNs by just applying a very systematic sequence of convolutions and max pooling layers. All the convolutions were with filter sizes 3 by 3, stride of 1, padding of 1. And then the padding there helped keeping the images of the same after the convolution. Right, so that padding of 1 is used to keep the size of this image after this convolution. The images still has that same size, 224 by 224. And then the max pooling has, for all the max pooling layers, they have filter size of 2 and stride of 2. So what they did was they trained this very large network. This is even like much larger than AlexNet. This is about 138 million parameters. So it's almost a little bit more than double of the size of AlexNet. This is from 2015. Right? AlexNet is 2012. So it starts with this like sequence of 2 convolutional layers. And here, because it follows this very standard pattern, or it follows a pattern here, I'm not putting the number of layers in the convolution. I'm just putting in parentheses the number of filters. So it has a sequence of 2 convolutions of filter 64, followed by a max pooling. So 2 of them, then a max pool. That max pool reduces the size of the image by 2, so it's 112 by 112 by 64. And then you have now convolutions of 128, 2 again. That's going to now change your filter size from 64 to 128. And then you have 2 of them, then you have a max pooling. That shrinks down again by a half the image, keeping the size of the number of filters. So now you go down, you have a sequence of 3 convolutions of 256 layers or channels, followed by a max pool. Again, that shrinks down your image by 28 to 28 by 28 now. And then you have again 3 layers of convolutions now by 512 channels, max pooling, and then another block that's very similar to the previous one, 3 times convolution of 512 filters. Then you have a final max pooling that takes the image down to 7 by 7 by 512. Okay? And then you have 2 fully connected layers and a softmax. This is also ImageNet. Okay? So this is a very kind of systematic way of building a CNN, and it still works really well. So you keep your hyperparameters fixed, so you don't have to think about what's going to be my filter size for layer number 4 and what's going to be my filter size for layer number 3. You just keep the same filter size and stride and padding for all of the convolutions and same parameters for the max pooling. And the pattern here is they're increasing the convolution or the number of channels in the convolution, right? So the volume is increasing by a power of 2. So they do 64, then 128, and 256, until 512. So it's a very systematic increase. And the pooling there is just shrinking the image by 2 all the time. So it's shrinking by 2 and increasing the depth by a power of 2 all the time. And it's an interesting paper because it kind of cleans up the hyperparameter space a little bit, because people are very concerned about, okay, how are we going to tune all these things? How are we going to figure out these values, right? So they show that just picking a standard or a systematic approach like this might work just fine. And you can, but see how the pattern of increasing the number of channels still remains and shrinking the image size also remains. That was true in LeNet 5 and is still true here in VGG60. Okay, so finally, and we have 10 minutes to talk about this is a little bit of a different network now. We're going to talk about ResNets or residual nets, or residual networks. They introduced an interesting component for CNNs. I mean, they didn't invent this, but they introduced this for CNNs. And what I'm talking about is residual connections, which are defined as additional links that connect some layer in a network to another layer that is not directly adjacent. From the beginning of the course to today, all the links we saw from neurons, they were from one neuron of one layer L to a neuron in the next layer L plus 1. And residual connections, they can skip layers. Let me show you with a diagram. So this is the type of structure we are familiar with at this point. This is kind of a snippet of a network, and you can think of this as a multi-layer perceptron or a CNN at this point. This is the intuition. You might have a layer L that gives an activation AL. And that goes through a layer 1 that gives you an activation AL plus 1. And then you have a second layer that gives you an activation L plus 2. That's the flow of the network, all the networks we've seen so far. So let me break this down a little bit. Every layer there has a linear and a ReLU, or any nonlinearity or activation function. But for the sake of the example here, let's just think of these layers as ReLU layers. So it's a linear followed by ReLU. Then you get activation L plus 1, another layer, linear and then ReLU, and then you get activation L2. So just to go a little bit deeper, right, the way we compute the linear output is WL1, L plus 1, times AL plus BL plus 1. And then the activation L plus 1 is just G, which is in this case is ReLU, right, of ZL plus 1. Just going very slowly here so you follow me, right? Again, for the second layer, I have exactly the same thing. I have the linear part, which is ZL plus 2, and then I have the nonlinear part, which is AL plus 2. This is the normal flow of a MLP and even a CNN. In the CNN, the only difference here is that instead of having this multiplication here, W times A, we have a W convolved with A, which is a convolution, which you can see as a multiplication. But what residual nets will do is that they'll skip a connection, or they will connect one activation to a layer that is not the direct adjacent next to it. And the way you combine this, or the way you skip this connection, is just by summing. Sorry, it's a little hard to see. But instead of computing G of ZL plus 2, the resnet, or the residual connection, what it's going to do is compute AL plus 2 equal to G of ZL2, which was the same as before, but now there's a plus AL. So you are summing that AL activation from layer L to generate the activation of L plus 2. So you are skipping the whole layer L plus 1. Okay, question? And in theory, you can skip more than one layer. Okay? You don't have to skip just one. But ResNet, this paper here, was doing it this way. Okay. So let's look at the ResNet, not the actual ResNet of the paper, but just let's think of a very deep neural network now. Okay? Now this one has 10 layers, but ResNet I think has much more than that. It has probably 100 and something. I'm going to open the paper. And the diagram here is just a simple, what they call plane, in the scope of the paper, they call the plane network, which doesn't have residual blocks or residual connections. And a ResNet, to build a ResNet, we're going to stack what they call residual blocks, which are just layers with residual connections. So what you have to do to make a ResNet out of a plane network is just add a bunch of skip connections. And they call these residual blocks. Okay? And this is important, guys, because actually the transformer today used the same idea. Okay? Not for images, but for text. But that's the idea. A ResNet is a sequence of residual, what they call residual blocks that look like this. And what they do in practice is they help dealing with the problem of exploding and vanishing gradients. What if we try to make a very, very, very large CNN? What would happen in practice is this. So let's look at this plot here. And on the x-axis, I have the number of layers. And the y-axis, I have the error of the network. And this is a plane network. This is a network, a very large network, without residual blocks. So in theory, what we expect is, and this is, sorry, training error. This is not testing error. This is training set. In theory, what should happen is the more layers I add to my network, the more it overfits. Right? If I keep adding layers, I'm adding more parameters, and it's going to learn the data. I mean, in the infinity, it has to memorize the data set. Right? That's what in theory it should do. But it doesn't do that. In practice, actually, you get something like this. So as yeah?
I did not change for as online.
So what I was saying is that in theory that doesn't happen. In theory that should happen, but it doesn't. In practice, actually, what happens is if you increase the size of your, or the number of layers in your network, you actually start to performing worse in the training set. In the training set, this is not test set. Right? Because the more layers, so again, X here is number of layers, not epochs, right? It's just making the network bigger and bigger and bigger and bigger. Okay. So eventually you start to diverge and like your model becomes worse. because the gradients probably are so bad that they mess up the whole thing, right? Because they're exploding or vanishing. It's a numerical problem, right? They are either too small or too large. They are affecting, you start to really mess up what you're learning. But this shouldn't happen, right? So ResNet really helps dealing with that problem. So what ResNets, in practice, they show that you can keep increasing the size of the network, and the performance of the model goes down and eventually converges as it should do. Okay. So this became very popular, and is a highly, highly cited paper. It was very influential idea. In fact, 1 year later, the transformer in 17 used the same idea to keep to be able to deal with larger models. Because as you'll see, a couple of weeks from now, the transformer architecture also has this idea of blocks that you combine or stack on top of each other to make larger networks. I'm going to finish by just showing you this paper. That's actually my last slide. I wanted to show, I have some notes here to show why in theory that actually helps. But I can put that in the lecture notes. But this is the paper. And actually here you even have right in the beginning of the paper, you have a slide discussing what I just mentioned in terms of training error. Here is a figure showing the residual block. Okay. And then there is some theory explaining why that happens, that works. So is this idea of identity mapping shortcuts. I'm going to try to put that in summary for you in the lecture notes. But if you want to understand why they work, you should read this section 3.2. And here's an example of a very large ResNet. Okay. So here in the leftmost column, you see a VGG 19, which is that VGG 16 we saw, but a little bit bigger. And then in the middle, you have what they call a plain 34 layer, which is what we just saw in the slide, which is a sequence of, let me show you, sequence of convolutions. Okay, here are the sizes, filter sizes, number of filters, right, 64, and then it's like the 3x3 convolution, and so on. And so the middle row there is showing what they call a plain convolutional neural network. And on the rightmost column here, you see the same network, but now if this is skip connections. Okay. That's the idea. That's what they proposed, and this really became very popular because it helps increasing the number of layers in a network. I don't remember from the top of my head the size of, let me see if I can see here, the size of the network they trained. No, there is even a ResNet 152 here. Okay. And they're showing here the top one error. So remember I mentioned when they're reporting error in image classification, they have the top one, which is getting the exact class correct. But there is also top 5 error, which is like, if you look at the top 5 predictions of your network, the most likely classes is the right answer there, right? So you give more chance to the network. So yeah, so in fact, this ResNet with 152 layers was better than the other approaches, right? Okay, that's what I had. This was a paper from 16. This actually finishes our discussion on CNNs. There's much more to talk about, but we don't have time. Okay, I decided to just put two lectures of convolutions because I want to focus on generative models at the end, and so I think this is a nice trade-off. All right, thank you, and I can take questions if you had.